Cek, cek, mic, one, two, cubaan suara, satu, dua. Cubaan suara, satu, dua, cek, mic, one, two, three.
Hello? Mm. Testing.
Hello?
Assalamualaikum dan selamat petang, tengah hari. Selamat datang kepada welcome to the School of Physics public talk. We are fortunate today to have with us Professor Dr. Chin Fei, who is staff at Taiwan National University of National Taiwan University, based in Taipei. He is here on holiday. He is a Malaysian from Johor. And he studied Form 1 to Form 6 at Fun Yu High School. And he carries the UEC certificate, the hotly discussed, debated certificate. And then he went to Taiwan to further studies. And from there, he went to University of Maryland for his master's and PhD. And right now he is joint professor at National Taiwan University, and he has done a lot of research, and his area of interest is in star formation. How he started, I had a chance to chat with him. His interest in astronomy started in 1987 when there was a Halley comet, and he was at school that time, and that fascination carried on, and he, took up astronomy as a profession. Okay, without much ado, I invite Professor Dr. Chin Fei to deliver his lecture. Thank you very much.
Hello? Can you hear me? Is it too loud or too? Okay. Okay. Well, thank you, Dr. Halim, for the introduction. Uh, by the way, you have to mention that I'm actually from Asia A. My primary institution is Asia A, Academia Sinica Institute of Astronomy and Astrophysics. And I also a joint appointment, a joint professor from the NTU. I have a point. Today I'm going to talk about the ALMA view of star formation. The hungry babies are eating a space hamburger and spinning bullets. And this is the ALMA. Yeah. This is the largest ground-based telescope so far. This is in Chile, 5,000 meters high. And this is the hamburger that I'm going to show you today. I think I need a pointer or something. Yeah. So this. It's coming. Okay. Okay. Yeah. Here is the introduction page. Our institute. So here's the building of our institute. In front of this building, there's a beautiful lake, and a nice environment to do research. And to have about 200 people. It's quite big. We have about 40 faculty members. We have postdocs. We have students. We have engineers, and also staff members, and office members. So altogether, it's about 200 people. Yeah. Yeah. Here's the ALMA. Give you some brief introduction of ALMA. So ALMA stands for Atacama Large Millimeter Sub-Millimeter Array, largest telescope ever built, inaugurated on 2013. March 13. You have two ports. This is called main array. They have 50 12 meters array antennas, and this antenna can be distributed in a 16-kilometer area. It's quite big, and it's a collaboration between the North America, including U.S., Canada, and Taiwan, and also the European countries. And this another part is called the compact array. It has 4 12 meters antennas, 12 7 meters antennas. This kind of at a fixed position. You don't move those antennas much. Okay, you have pointers, good. Yeah. Thank you. So this is the East Asia contribution, including Japan, Taiwan, and Korea. So Taiwan joined this project through 2 channels. One is through the North American channels, the other is through the East Asia channels. So Taiwan had open access to EA and the NA times by proposal. You can write proposals and apply for time. Here's the time share in each region. So we have the East Asia about 22.5% of the time, and for North America we have 33.75%, Europe 33.75%, and Chile 10%. This kind of international collaboration, yeah. And Taiwan has open access to these 2 regions. So the total time that Taiwan people can get is, can see, add them together is 56%, something like that. Yeah. So ALMA proposal may also be submitted by PI whose affiliation does not lie within any ALMA region, like the Malaysia. Malaysian people can write proposal and submit to ALMA, and those proposals were considered as an open sky proposals. Can be a few percent of total time. So this is Chile. So it's the Atacama Desert of northern Chile. Yeah, this is Chile, the northern Chile. Yeah. So this on top of the this is the plateau, the Atacama Large Plateau, 5,000 meters. The arrays on top of that. This is one of the driest places. But we usually are observing remotely from 2,900 meters high here at the operation support facility. Yeah, so this is 5,000 meters. It's about 26 kilometers from the operating area. Yeah. So this is a bird view of ALMA. Yeah. Yeah, with snows, of course. Yeah, this is snows. The bird view of ALMA. Yeah. So one question you want to ask, what's different between Hubble Space Telescope? Because you know a lot of Hubble Space Telescope, right? You see images from the Hubble Space Telescope. So the first thing you want to compare to is the Hubble Space Telescope. So the highest achievable resolution can compare is Hubble at 0.05 arc-second. It's very high resolution. But ALMA can go up to 0.005, which is 10 times higher resolution than Hubble Space Telescope. Yeah. But in different wavelengths. This is mostly in optical, infrared, and some UV. And this is in radio, mostly millimeter and some millimeter. And the thing they can see is different too, right? Suppose this is the optical image from the Hubble. Into to this star forming region, see a disk structures, see a central stars, and the stars, and it's surrounded by dark area, dark shadows. Because of dust extinction, you see in optical. But if you look at it in ALMA, with ALMA in millimeter wavelengths, you see this inner part very bright. This dust continuous emission. You can see the dust, the particles, dust emission from the disk. You can even see, maybe we still looking for the planets, protoplanets. Maybe see some protoplanets as well later on. So kind of see different things. So optical and in radio, they're seeing different things. So kind of complementary to each other. The optical seeing by the outer these bright regions, the hot regions, but the millimeters seeing the cold regions. So this is one example. Okay, this is the process made by our institute. I want to show you what can we do with ALMA. There's many things we can do with ALMA. You can start from the Big Bang, the microwave backgrounds, all the way to the star galaxy formations, star formations, planet formation, life formation. Everything that you can think of. Everything that's cold, that's cool, you can map it with ALMA. It's so sensitive. High redshift galaxies, even molecular line emission from high redshift galaxies, we can map it with ALMA too. So this kind of the kind of introduction about ALMA. So now going to my science. I'm doing a mostly star formation. So this is kind of classification of star formation. Different stages. I have class 0 stages. This is the frequency. This is energy plot versus frequency. At the early phase, all the material here is quite cold, so the peak at lower frequency. The kind of cold cloud collapsing. And at later phase, we call it class 1 phase. This kind of protostar started at the center and kind of surrounded by disk and envelope, kind of heat up the gravitational energy, release heat. So move the peak of the spectrum toward the higher frequency. What? Something say anything? No? Sorry. So this is protostar, and this is the surrounding envelope and disk. And when you go to class 2 phase, all the envelope material is gone to the center part, or either go to the center part or eject it away to the ISM, and leaving it behind a center stars surrounded by a protoplanetary disk building the planets. So at the class 3 phase, it has this leaving this debris disk surrounded by these planets forming disk. Later on, it becomes the solar system like our own. Okay. So this is another view of this star formation. This is from a big cloud. When they collapse, when they collapse, it not only produces a single core, it also produces many cores, actually dense cores, because when you collapse, the Jin's length, the Jin's mass becomes smaller, and then fragment into small pieces, small dense cores, and each dense cores will become star-forming region system, and then this is class 0 phase, and then forming a disk around the protostar, feeding the center protostar, and some material kind of ejected away, shoot it away from the. You kind of wonder why it happens. Why is everything supposed to fall into the center protostar instead of some of the materials ejected away? Why, right? And later on, looks like this, right? All the material, surrounding material, kind of falling into this, and this jet kind of open up, become a wide-angle winds instead of collimated jets, and later on become this protoplanetary disk building planets, and then later become these solar systems on. Yeah, today is mostly talk about the early phase, because this disk, always see that this is coming from this early phase, right? And the early phase, we don't know much about the early phase because in the past we don't have the high resolution to look at those early phase, what happened in the early phase. But with ALMA can see that. So this and jets are formed in the early phase, in this phase. The detailed process is complicated, but angular momentum. So that's why you form a disk instead of a sphere, right? Fitting the center protostar. And also B field, there's many fields inside this. So still unsure when and how these jets are formed at the beginning. Yeah. So recent high resolution of ALMA can go down to 10 AU resolution, very small size scale. Can zoom into this inner part. Yeah. Our solar system is about, the radius is about 50 AU something, right? So you need high resolution to see that. Yeah. Also high sensitivity can go down very deep of the faint materials. Yeah. In submillimeter wavelength. Why we need submillimeter wavelengths? Because it penetrate down to the inner part. So this all combination allow us to see the detail of this disk and jet formation, which is still not clear at the moment. Yeah. And so there's some observation I want to show you. This is the former it's very nearby systems. Yeah. And this is Hubble, the blue one, scatter light. And this orange one is the thermal emission, propping the material itself. It's not just the scatter lights. It's the heat, it's the radiation from the heat of the dust. Yeah, yeah, you see beautifully. But this is a very early phase of ALMA, taken by early phase of ALMA. Now the whole circle is very sharp. Yeah, sharper than this. Yeah. But I think this is still very important difference between the HST and the ALMA images. So we look at this beautifully. And this is later phase, class 3 phase. And when we go to a little bit earlier, in class 2 phase, some observations. The TW Hydra, 10 million years old. The central star has a mass of 0.8 solar mass. You see these concentric rings. It's kind of surprising when you see this kind of image. This looks like this looks like a model instead of observation, right? When we see this kind of image, we're kind of surprised. Wow, is this an image or is this model or a observations? Yeah, it's quite surprising. So each ring may have some a protoplanet forming in the ring and strip up a rings, clear up this ring regions, so appear as a ring. So this is a 22 AU gap. Yeah. To show you the size scale, so this radius is about 50 AU, so just like our own solar systems. Yeah, it's amazing. Yeah. The other one is Hubble space. This go to younger one. HL tau is 1 million years old, so 10 times younger than that. What we see? Yeah, we see. Of course, we'll see some jets now. Yeah, still active in creating material. So, but even this is the Hubble Space Telescope to show the jets. But at the center, you don't see much. It's so bright there in the optical. Yeah, but not much you can see toward the center. But when you zoom in with ALMA, there's also early phase ALMA observations. You see these concentric rings as well. So even at this age, young age, you see this protoplanetary disk forming already. And these rings each ring may be caught by a protoplanet something. Yeah. So you can see a difference from HST images and the ALMA images. So this is also the size scales, 32 AU, the size about 100, a bit bigger, yeah, than our solar systems. I mean the disk. Yeah, okay. So how about the early phase? Look at this. The disk here is so thin and concentric rings. How about the early phase when material is still actively accreting toward the centers? Yeah. How does this formed? In the early phase might be actively accreting, right? This phase maybe you see some jets, but actually the mass loss rate is quite small already. Yeah. So the early phase, I like this constellation, Orion. Yeah, look at this constellation a lot, and I like it. This is the image that, by one of my colleagues on top of Malacca. Yeah. And we zoom into that other part here. Just go to a little bit younger, a class 1 source. Now the accretion is much active and injection is much active. So you see more prominent jets on the center part. Yeah. And zoom into that part, we see a disk also. Now it's a disk, but we don't resolve it at this moment. Yeah. We kind of resolve it along this axis, but not this axis back then. Yeah. So we look at this systems. We try to understand what happened to this system. What produces the disk? How the disk is formed? We need to look at the kinematics, right? It's rotating disk. How does this form? So we look at this gas in C18O, these CO isotopes. With ALMA, this is the size scale, 7,280 size scale. Very big, right? Yeah. And the mass about 0.3 solar mass. And we zoom into that center part, we see this the dusty disk. It's not just a disk, it's actually rotating. So we have this kinematic information of the disk. Yeah, it's rotating. Blue shifted here, which means material there is moving toward you. And red shifted material here, which means moving away from you. So you see a rotating disk right like that, moving, yeah? Accretion. This kind of almost edge on. So just like here, like this, so like it rotating like that. Yeah. So it's a kind of edge on, no? To you. Inclination angle is about 11 degrees. So 11 degrees away from the line of sight. So they kind of edge on. You see the disk nicely and the rotation nicely. Yeah. But why the material is so big, but the disk is so small? So that's the question I want to ask. We have been looking for the solution for a long time, because the older disk we look at is about 500 AUs most in size. Why so small? But the cloud is so big, but the disk is so small. So we look at this and zoom in to the inner part here. We see some very interesting phenomena. This is the plot of the distance here to there, and the angular momentum of the rotating material. Angular momentum of the material. Yeah. Material here, yeah, inner part. You see the angular momentum at the outer part is kind of constant. So the material kind of fall in with constant of angular momentum. But later on, it decreases very fast for some reason. I'm not sure what the reason is. And then form a disk at the inner part. So that's why you see a very big ambient material around it, the cloud, but only a small disk around the center source, center protostar. So this somehow the angular momentum is lost. But why is the angular momentum lost? We don't know for sure. But one way to do that is through magnetic field. So because the clouds, it contains magnetic fields. Suppose it's a cloud. Yeah, this is an observation toward NGC 6334 cloud course. So this is a cloud course, and you see the B fields. The line here is the B field orientations. So you can see this flattening structure, the flattened structure, and that's threaded by the toroidal fields. This toroidal fields, you can see toroidal fields. Yeah, the size scale is quite big, 1 parsec scale. Yeah, and then you go to the small scale, few thousand AU scale, less than that, 1,000 AU scale. You see this few lines kind of pinched, the material going from here to here, and drag the few lines in. The few lines frozen in, going to that. So make it appears like the few lines appear as a hourglass. Yeah, we call it hourglass morphology. This is called hourglass morphology. So this is a cartoon showing this kind of things, observation. So there's flattened structures and extended envelope. You don't see that here. Yeah, but you see the few lines. Yeah, this inner part here, outer part. Yeah. So kind of call it hourglass morphology, is a standard hourglass morphology because of gravity pulling material in toward this direction preferentially. Yeah. So we do some simulations. People have done some simulations. Look at this quadrant. Yeah. So suppose beginning all the material falls in radially, or some guided by the few lines. But if you evolve this material, what will you see? You see something, some outflow material. Yeah, the material is carried away by these small, slow outflow. Yeah, you see these the vectors going out. These are outflows. So the material is actually carried away by slow outflows and carry away the angular momentum away from this system here. Why is that? Because there's a few lines. When you collapse the material, because conservation of angular momentum, you move faster, you rotate faster, right? But the few lines will try to stop that. Yeah, twist it back, right? So this is called magnetic braking. So the magnetic braking will will remove the angular momentum away from the system. So this could be one possible solution to that. Why? Because look at cloud, only see a smaller disk. Yeah, such small compared to the cloud size. Well, this is the problem that we solved with the ALMA, and there's a few more problems solved with ALMA. Yeah. So this is another one. Alright, go to a younger source, so you can see better. See the inner part, the younger phase. What happened in the younger phase? This is Orion constellation again. Beautiful jets coming out. This is even more active. This is in H2 emission. This is taken by the VLT telescope at 0.34 arc-second resolution, more than 10 years ago, 20 years, almost 20 years ago, 15 years ago. So you don't see anything here. It's kind of dark here because at this phase, younger phase, there's a lot more material, ambient material there. Yeah. So you don't see anything in the infrared. This is in the infrared image. You don't see much at the center. So this is a class 0 phase, a protostar, a solar mass about the mass about 0.2 solar mass. Much younger. The earlier one is like 1 million years old, and this is 40,000 years old only. Yeah. So go to the younger phase, you see something interesting, more interesting, and where this is formed, when this is formed, and jets form. So this is the zoom into the inner part of the system. See the jets. You look at in ALMA, you can see all the way the jet all the way to down to the center part now, because in the radio you don't suffer the dust extinction, not like the infrared. So you can see the jet all the way down to the center part, very nicely, and And when you look at ammonia gas, you see a big envelope. Now you know why there's a dark land in the infrared, because there's a big cloud here. Yeah, dense core here, a dusty cloud. Okay. And also, this is when you zoom into the inner part with ALMA at very high resolution, you see a flattened structure. You see some tiny structures here, elongated, perpendicular to the jet axis. So you see this, and zoom in to that, blow up of that image, and rotate it a little bit so that the jet axis is aligned with the vertical axis. So this part is so bright, we still don't know whether there's a disk inside or not at this early phase. Yeah. So is there a disk inside? What kind of structures the disk is? Is it rotating? And what about this ambient material, this flank structure doing? Yeah. So we zoom in now. We zoom in to very high resolution, 0.02 oxygen resolution. You can see now this resolution is higher than Hubble now. Hubble is at 0.05 oxygen at most. The 0.02 oxygen, 8 AU resolution. What can you see? You see, we do detect the disk, the dusty disk, for the first time. Yeah, at this early phase, for the first time, see these kind of disk structures. Yeah, and you see a dark line as well, and the size scale about the Neptune size scale here. We call it Hamburger. Why you call it Hamburger? It looks like hamburger. Yeah, this is funny things. So this is Hamburger. So because it's bright here, it's dark here, and bright there, and bright here. It's kind of tilted toward you because it's slightly tilted toward you. This kind of slightly tilted toward you. You see the upper part brighter than the lower part. So I call it Hamburger. Yeah, I think this is very interesting, exciting results. Yeah, we haven't seen this before. Yeah, this first time we see this kind of data and resolve it. Yeah, and vertical structure as well. And of course, not just the image, we want to model the emission. This is a dust emission. Yeah, so model single accretion disk model. Yeah, this kind of disk model and the temperature. And this is a temperature model, right? Temperature cooler here, brighter here. It's because it's brighter in the surface because of radiation heating from the protostars. Yeah. So this cooler part give you this dark land, and brighter part give you the surface, give you the bright upper part and lower part. And when you do a calculation, it gives you this kind of similar structure that you see in the observations. It's very exciting, yeah. But this is. When you look at this, you still think this is much better than this one. It's much prettier than this one. Yeah. So the CBS News, also excited about this news. So they say space hamburger spotted in astronomy first. Yeah. I like this. The title. Yeah. Space hamburger. I call it hamburger, but I call it space hamburger. I think space hamburger is more better. So hungry baby start eating a space hamburger. But the main point is the accretion phase. This is geometrical thick instead of geometrical thin, because this is actually accretion producing a lot of turbulence. Maybe we don't know for sure why it's so thick instead of thin disk. It's so thick, puffy. A lot of things going on: turbulence, heating, also the accretion heating. Static radiation heating and turbulence, so make it so puffy. The next thing is this is rotating or not, right? So look at the with ALMA as a similar resolution. We saw this redshift emission. Look at we detected a very complex organic molecules. It's not just simple molecules. Very complicated organic molecules. Like the methanol, deuterated methanol, CH3SH, formamide, deuterated formic acid. Yeah. So this also very interesting, very exciting too, because we haven't seen this kind of organic molecules, complex organic molecules, in the size scales. Yeah. And you can see where these molecules are now. you can see it's on this atmosphere on top of the disk for the first time. Yeah. And this is kind of also prebiotic molecules. We have nitrogen, with carbon, with oxygen, with hydrogens. So all you need to produce life. Organic. So, but anyway, before that, also this rotation. This is blue shifted one side, blue shifted on this side, blue shifted on the other side. It tells you that this is rotating with the Kepler rotation. So this Kepler rotation gives you a mass of 0.2 solar mass something, as we predicted before. And the nature is so excited about this discovery as well. So they wrote an article, short article about our discovery. Yeah. So organic molecules spotted in star forming disk. Yeah. This is we asked our one of our colleagues to make these figures. They kind of started with a Chinese what's that called, water painting something, and then use Photoshop something, to modify it, become this. So another thing they want to ask is, how about the surrounding? Now we know that this is forming, accretion disk is forming, and also it's rotating. But what about the surrounding material? How does this material become the disk? Yeah, it's very important, right? Because ALMA now have the resolution to see that, to the inner part. So we can zoom into that part in the SCO plus molecules. These are ions. Ion can follow something, right? Can follow the magnetic field, hopefully. Yeah, so we zoom in because the star formation regions is affected by the magnetic fields. If we pick up, choose a right molecules, we can trace something of the magnetic fields too. So we pick a CO plus. Yeah. So we see this. Look at the ambient material. We see something very interesting. This is a spectrum. This in the envelope. This is the inverse p signet line profile. If you have looked at this profile before, this is a very exciting profile as well. This tells the material is infalling toward the center. Yeah. So suppose you have a cloud, loss increasing toward the center, and infalling toward the center, and this blue shaded part. You look at the cloud from here. This is blue shaded part. This is red shaded part, and this give you this emission, and that give you that emission, and this give you this emission, and that give you this emission. But here, the material here, is it working? Okay, the material here is absorbed by cooler region here. The material here, the radiation from here is absorbed by the material here, which is cooler. So make absorption here, make it dimmer here. So you see a brighter blue shifted emission than the red shifted emission. And this is the signature of the info motion that people have been looking for. But the ALMA is so nice; it gives such a beautiful signature of the info motion. Yeah, directly. Yeah. So see this. We're so excited to see this. Yeah. But this is even deeper than that because here doesn't have this inside this envelope, but here we see a bright this inside the envelope, and then produce a very deeper absorption. So another thing that we look at is rotation, whether this envelope has rotation or not. Because when you produce a disk, you need rotation as well, right? So you need to look at whether it's rotating or not. So the envelope is turning around so that we can do a study. Yeah, cut along this axis. Look at the kinematics. This is the distance from the central star, and the blue shifted velocity and red shifted velocity. You see these triangle structures. Triangle structures. And this is also shifted. Here is kind of shifted toward this direction. That shifted toward that direction. This is kind of interesting as well. There's some signature here. Suppose you have info motion. You see this. This is from the back part and from the front part. You have rotation. You see this. Kepler rotation. One side is red shifted. The other side is blue shifted. So when you combine them together, you see this triangle structure shifted, from the center position, from the star position. This is what we saw here, yeah. But there's a self-absorption here, yeah, because here's just a optical thin model without considering the absorption effect. So here, the absorption effect, absorb the emission here, but the basic structure is the same. So we see the emission, the materials is in falling towards the center. So I build a model here. So it's a disk that we see, the Hamburger, and this atmosphere and the surrounding envelope. We can identify, we do a detailed kinematic study. We can identify two radius. One is the centrifugal radius, which is the radius at where the centrifugal force is balanced by the gravitational force. Okay, and this centrifugal barrier is all the kinetic energy is converted to the rotation energy. So in that place, in that rotation, you don't have material falling in, kind of stagnate over here, kind of some push a little bit, you can go into become a disk. So this is the model that we come up with. And then this kind of thing model can fit the data pretty well. Because today it's kind of, I didn't show it, the detail modeling here, but just show it the structure of the model. Yeah? But it fit the model pretty well, the observation pretty well. The other things I want to show you, this is a little difficult. Let me see so I can explain. This is the SEO plus. Yeah, this molecule that we choose, this molecule because we want to see if there's any effects of magnetic field that we can see from this observation. So I do a cut here too, and see this absorption around this systemic velocity, around this systemic velocity. Yeah. The redshifted part and blueshifted part. Sorry, the systemic velocity here. So the absorption band here. And why the absorption band? It's from the surrounding material, the extended material. Yeah. So it's from the extended material here. Yeah. There's a magnetic field threaded in the surrounding material, extended material. So if the motion of this material is guided by the field lines, yeah, can motion along these field lines, then we see this material mostly in the redshifted. If you look at this from here, and this mostly in the systemic velocity. So in that case, it can produce this kind of absorption band. So it kind of suggests that the material surrounding the disk, the center, the motion is guided by the field lines. Okay, so we have tell you many things about these ALMA observations, the results, and this is another thing. The jets, we see the jets coming out from the disk. What produces disk? Why there's a jet coming out from the disk? This supposes the center protostar, and there's a disk, and the field line threaded the disk. Because this is rotating, right? This is rotating. So if a field line is threaded into the disk, if you turn it, the disk, as fast as possible, what will happen? If the material is loaded here, it will get flung out along the field line, right? It will get flung out along the field line. So the material will go out. It's rotating, because magnetic centrifugal force. Rotating it, material will go out, gets flung out away from the disk. So this produces the jets. Yeah. So there's two different competing models. From they call this wind and they call this X wind. X wind is only from this X point only, one single point truncation. The disk has truncation radius around here, and this co-rotation with the center protostar, and this field lines there. And the disk outside here is no field lines. Yeah. So in these two models, we can tell the difference from the observations, because the material can carry different amount of angular momentums. Because the angular momentum from the disk here has larger angular momentum than this point. Yeah, because the angular momentum kind of decreases with the radius, right, of this material. So a larger radius will give you a larger angular momentum. So when you measure the rotation of the jets, you can tell where the jets launched. So we can measure this rotation. So jets and this Hamburger. And in SIO, the molecules, SIO is good to trace this jet because it has it's a very dense density tracer, and trace up to 10 to the 8 particle per centimeter cube. Yeah, so you see this jets material, and we measure and plot these blue shifted and red shifted separately. You can see this blue shifted one side of the jet axis, and red shifted on the other side. You see the spinning jets. Yeah, spinning jet, it's just spinning. This is the first time we saw this kind of beautiful jets spinning motion. Yeah, because we have this resolution, 0.02 Austin resolution. Yeah, better than Hubble, 3 times better than Hubble. Yeah. So I can measure the angular momentum the jet can carry about 10 AU coulomb per second. So which means this trace all the way back to the innermost part of the disk. So we think that the rotation tells you that jets actually from the inner part of the disk. The purpose of this ejection of material is to remove the angular momentum from the inner part. See, I show you the model, the cartoon. Yeah, this spinning bullets coming from the inner part, and this is only from the very inner part of the disk only. Yeah, so material when they go into this fitting center star, the angular momentum got to be some part of the angular momentum got to be ejected away. So every time you take a bite of the hamburger, the disk, you're spinning bullets. Yeah, so we call that. So this is very interesting. So this is the Nature astronomy also feel excited about this result too, and they have the cover page about reporting our results. Yeah, so spinning bullets from a young gun. Yeah. So the whole picture of the star formation from the ALMA, with this so high resolution and persistent resolution and sensitivity, we can zoom into the inner part and kind of propping the problem. Yeah. So info motion of the standing material, guided by few lines and forming the flattening structures, infalling toward the center with conservation angular momentum, and somehow make the few lines here can take away part of the angular momentum and convert it into a accretion disk. And this accretion disk, at the inner part of the accretion disk, will launch a jet, carry away this inner part, the angular momentum from the inner part. There's one piece information missing. This angular momentum from the outer part of the disk to the inner part of the disk is different, right? Yeah, the outer part of the disk has larger angular momentum than the inner part. How does this angular momentum carry away? We still don't know for sure at the moment. It could be some mechanism. Yeah. So we look at different molecules, so tracing the disk material, the alpha material. We see something coming out from the disk as well, not just from the inner part of the disk, but also from the outer part, extended part of the disk as well. It's also rotating, and so the velocity there is smaller. Yeah. Yeah. So the jets over here, and see the rotating envelope, rotating outflow from the disk. And this can carry away the angular momentum from the disk as well. So it looks like we have the whole picture of this star formation, but we still need to confirm this because here the rotating outflow could be due to some other mechanism, like the inner part of the disk of the wind. Like the X-ray model, the winds coming coming from the innermost part of the disk and pushing away the disk material away. So pushing away, forming this rotating. So it's not directly from the disk. It's actually pushing away by the inner wind. Yeah. So I'm not sure the moment. So, but more likely to this wind. Yeah. So if there's this wind, then it's good. Then solve everybody. Solve all the problems. Another thing that I want to tell you is that so we know the formation of the accretion disk. Yeah. Now we go to see how is the disk size growth. Yeah. So we can go to early phase even go to younger phases. Yeah. So this is the Perseus IC 348 region. Another younger jets. Yeah, a younger one. It's about the center protostar only has a 0.05 solar mass. It's kind of brown dwarf mass. Yeah. It's 5 times less than the previous one. The class 0 is very small, yeah? Very young. The jets coming out from here. And this is the envelope, big, very dense envelope, flattened envelope structures. So into that in the dust emission continuum, yeah. You also see something very interesting. We see a disk, yeah, this structure. This is also an H1. We choose H1 disk because it's easy to see. Because we have different purposes. We can look at for the vertical structures. So this is orientation of the jets. So see this disk. Zoom in. This is resolution. So this is resolved in this direction and also this direction too. But we don't see this Hamburger structures. But maybe because the resolution is not high enough. Yeah. Maybe it still look like a bun instead of hamburger at the early phase. Yeah. But anyway, you can measure the disk size. Yeah. In this early phase. And we can also measure the rotation too. We also see some outflow, rotating outflow coming out from the disk. Yeah. But there's also atmosphere too. So atmosphere, the rotation atmosphere can give you the mass measurement from this rotation. So it give us a mass of less than 0.05. It's roughly the same as we predict before. So consistent with what the mass estimation is consistent with our previous estimation. Yeah. So we can plot this. Yeah. This radius versus the mass of the center protostar. You see a train. We can plot other objects too. Yeah, this object I told you, I mentioned this to you. That's other objects, class 0, class 1, later phase, clouded here, but not much here because it's not resolved before the ALMA era. Now we have the first one resolved with ALMA. Later on, I'm going to study this 3 and see what the disk radius are. And then, but from here, from this point, data point, we already can see some train already. You see this, the disk is size growing with the mass of the protostars. Yeah. If you can resolve these two, and these two can fall into this green lines, then we can confirm that. Yeah. But so far, we cannot confirm, but just a suggestion that the disk grow with the protostellar mass. This is very interesting, yeah, because they tell you the early start, slow growth. It's more consistent with this model instead of this model. Yeah, this model is a cloud with a solid body rotation, and this cloud with a kind of constant angular momentum. Something is what we see in the observations. Yeah, so it's kind of nature to expect this to be consistent with this curve. Yeah. So that's all the things that I've done for the star formation part, early phase. I've done other parts as well, but I think those are very interesting results. So, and also when you carry away is this this slide. So for star formation, hungry baby stars eating a space hamburger and spinning bullets. And we have these summer student programs in Taiwan, in Asia, every summer time for 2 months, from July 1st to the end of August. Yeah, our faculty members, we have 40 faculty members. About half of them will provide some projects to the students to choose from. They can apply, and then can have interview and a selection, and then you can. The students selected will come to Taiwan to do a 2 months summer programs. We'll pay you the salary of 20,000 NTD per month, and also provide private lodging as well. Yeah, it's a very nice experience. You can go to Taiwan to work with us for a short period of time. If you're interested, you can continue. Yeah, that's it. I mean, that was kind of talk. Yeah, I should introduce my institute to you more, but today I give you more about the size of my. If you have any question about the institute, you can ask me now. And by the way, I want to tell you something. Introduce Kevin. He's our postdoc in AJA, and he's from Penang. He's from Penang. Yeah, he's came here. He's back for vacation. Yeah. Okay. Okay.
Thank you very much, Professor Lee. Anyone who has questions can direct ask questions.
A question from you.
Just now you mentioned angular resolution for ALMA. How much is it?
The highest can go is 10 times higher than HST, and go to 0.0052 5 million arc second.
It should be in terms of arc second.
Arc second, yeah.
The one that you mentioned that it's 10 AU. Does it maintain the 10 AU?
Yeah, it can. Yeah, multiplied by the distance. Yeah. Yeah. Suppose to add 400 parsec. So 0.02 arc second is about 8 AU resolution. Okay. So the observation I gave you, show you, is very high resolution. It's very haven't done before. This is the longest baseline, 16 kilometer baseline resolution. Yeah, the largest. We cannot go further than that now. Yeah, we had to wait for the high frequency to go to higher resolution. Yeah, but it's not over yet. Probably next cycle. Yeah. Any? I see one hand. Yeah.
Do you do the simulation of star formation with computers to compare with the observation?
Yes, yeah. What part of observation you're talking about? Yeah, we are now collaborating with people in US. They're doing this disk simulation, how the disk is formed with magnetic fields, global simulations. Usually, in the past, when the computer power is not so high, they only simulate part of the disk. But now the computer's resources so powerful, they simulate whole disk, with the magnetic field, and then they see something like that too. Yeah, they see perfect disk, and then if you do the radio transfer, you can see some dark line as well. Yeah. So this coming actually in August, I'm going to US to talk to them about this new results. This kind of new results here. Yeah. Yeah.
Just now you mentioned the magnetic field line.
Yeah.
Magnetic field line of the stars.
The disk coming from the the magnetic field line. You mean in the cloud itself? The cloud galactic magnetic field line, galactic fields. Yeah. But when it collapses, the magnetic field drag in, flows in with the collapse. So as the ALMA collapse, the field lines also collapse too. Carry inward from the material, from the cloud. The cloud itself already it's magnetized. The cloud itself is magnetized. So as it collapses, the field lines also falls in as well. But not all the material, many field lines get carried in. Some of them must have diffused away. Otherwise, because when you the B field were getting bigger and bigger, stronger and stronger, stopping the collapse. So the B field had to be diffused away. We call it bipolar diffusion. Yeah, diffuse away, and also this magnetic braking as well. Yeah, if the magnetic field can all the way falls in, then the magnetic braking will be very efficient to preventing the disk from forming. Yeah.
So Dr. Lee, can we say that with this ALMA is the beginning of this study of accretion of this sunlight star? So in future there will be even more
Yes, this is the kind of
It's a new tool. Yeah.
kind of
a new technique.
new results on the first case showing this. We are expecting more and more and more this kind of case coming out soon. Yeah, we having starting this big project, hoping can get some more time from ALMA to look at more objects to see this kind of accretion phase in the early phase. Yeah. Yeah.
Just a quick one. It seems the main feature you're looking for to look for the accretion is the ejection of the gaseous material stream.
Yes.
Is that a standard feature for all accretion disks?
Looks like it at the moment. Yeah, at the younger phase, we see a lot of jets coming out from the star forming regions at the early phase.
So we can say that it is basically a feature of that.
A feature, kind of a what's it called?
Indicator.
Indicator, yeah, kind of indicator of star formation. Yeah. And also the disk as well too.
Jerry, you have a question? Jerry?
Yes. Dr. Tilly, apart from spotting the space hamburger, what, in your opinion, your own view, are the other biggest achievements that ALMA has notched up so far in its history?
Besides this,
Besides spotting the space hamburger.
there's the rings. You see it's star formation, right? So this and planet formation. And the key projects of ALMA, one of the key projects look for the planets to directly detect the protoplanets. So far we had not detected anything yet. Hopefully can spot, luckily can find some objects, detect the protoplanets. Now that one is this one. Let's show you. Yeah. Look at this one. Yeah, I'm also working on this one too. We're hoping to see some planets here. The planets. You see this ring, so sharp. This must be shepherded by planets, right? There might be some planets around here to guide this, to form these sharp rings. Yeah, shepherd, right? They call it shepherd ring. Yeah, this so sharp, so narrow. How come? Yeah, there's maybe some planets too. One inside, one outside. And Hubble space spot some candidates, but not confirmed with ALMA. Haven't confirmed with ALMA yet.
What is the minimum angular resolution required to observe the protoplanets?
We won't be able to resolve it, but we can detect some emission, the bright emission. Yeah, hope we can detect some dot moving, yeah, bright features here. Yeah, we probably even can detect some protoplanet. I know, sorry, protoplanet disk. The disk around the planet. Yeah, here's a protoplanetary disk, right? Surrounding the star. Suppose there's a disk. There's a planet here. There must be another disk around the planets too. That's another thing that you want to do. Yeah, hopefully can do something. So this is very important discovery, and also this is a very important discovery too. We haven't seen this before. This is not my work, but other people's work. So beautiful, just like models. Now people want to confirm these rings are actually produced by the planets or not, or some instability or planets. Yeah, but of course people tend to like the planet mechanism, right? It's more sexy that way. People like that, right? Yeah. But so far I have not confirmed that yet. And also this case, even in early phase too, they see this class 1 phase, they see this concentric rings as well. People also want to confirm whether it's produced by the protoplanets or not. So this, I think the major achievement of the star formation also discover the prebiotic molecules, more like sugar. They even discover sugars as well. Sugars, yeah. and very complicated molecules. Yeah. And of course, they want to look for even more complicated, like glycine. Yeah, glycine. If you want to look for glycine, yeah, if they can find glycine, that's even more exciting. Yeah, and then probably even more what's that? Produce it live. I think that's the let's see what else for in the star formation. I think that's so far that's it, I guess. Yeah. But in other fields like Einstein rings, beautiful Einstein rings. You see this with ALMA, beautiful rings. And then can use the ring to constrain the lensing galaxy, the mass of the lensing galaxies. Yeah. And also what else? High redshift galaxies. High redshift galaxies, because so sensitive, you can detect the quasars and also the line emission, the CO line emission at high redshifted, and you can detect CO lines in a big field of view, so you can detect many the lines of many quasars. You can do a statistical study, yeah, instead of just one by one. You can do a survey easily. Yeah, it's so sensitive. You can map an area and pick up all the lines from all the quasar there and do a statistical study. It's so amazing. And see the redshifted, the line, you can plot the peak, the spectrum of the redshifted, the Z value in one shot. Yeah, so amazing. It's so sensitive. Usually, before we just take one by one, but now you can take whatever in your field, but 20, 30s, just have the spectrums and plot the Z values, spectrums. You can see the beautiful. Yeah, I think that's very important. Yeah. What else?
One question.
Okay.
Has ALMA ever seen any T-Tauri phase of proto?
Yeah, this is T-Tauri phase. This is almost T-Tauri phase. Yeah.
So this is the T-Tauri phase?
Yeah, T-Tauri phase. Class 1 phase, and this is the T-Tauri phase. Yeah.
Oh, so produces the century.
Yeah, so amazing, right? This is close to T-Tauri phase. In HR Tau, see that? So this is kind of a surprising, right? Before the ALMA era, you probably see just a blob. Yeah, I see one thing, and the whole thing just one pixel, a few pixels only. 1 to 2 pixels, probably too exaggerated, probably 10 pixels. Yeah, but now you can see the structures. Yeah, here is even better, right? See this? Yeah, this is so amazing. So just like model. Yeah. Yeah. So now we see a lot of this now, not just one. You see many of this now. And also spiral structures in the early phase. When you look at different orientation, you probably see some spiral structures here too. Yeah. But not for this object, for different objects. You see spiral structures. Yeah, I think those are very interesting, very new results. Yeah, I will add to that. The spiral structures also new results. And also, what else? The source that originally thought is one single source, but at high resolution becomes 2 or 3 sources. Yeah, binary is a multiple something, and see spiral structure coming linking to one of source. Originally thought just one disk and one center polar star. But with ALMA, I see, actually it's not one single star, actually 1 or 2 or 3 even. And the disk that you think is a disk actually spirals. Yeah. Yeah, I can see 3 polar stars and spiral structures. Yeah, it's quite new. Right. Yeah, those are very new things. If you want to ask a question.
Do you have any theory or model how the organic molecules are formed during star formation?
Yeah, I don't have. I'm not expert that field. Yeah, collaborating with other people in Europe, they have the expertise. Yeah, so usually the chemistry part is expertise of the Europe people. They can help us to figure out how these molecules form. But usually you have warm material, warm region, warm layer. Yeah, and yeah, high pressure something. Yeah, warm area. Yeah, this you see this atmosphere. Sorry, here we go. It's quite warm. You see the temperature here. I show the temperature. Yeah, it's quite hot. 332 Kelvin. It's warm. 167 Kelvin. It's kind of warm material. Yeah. So maybe some heating sources you need. Maybe it's the stellar heating or something. Yeah. Shock heating something. Yeah. They have the chemical network. I think the European people, they have chemical network to produce this kind of complicated molecules. Yeah.
Okay, one last question.
So this is to study accretion disk of solar system within the Milky Way galaxy. Can we apply the technique to study accretion disk of galactic centers or galaxies far away from us?
No. So far, no. This is very nearby. You have to
Nearby,
do
yes,
it.
yes.
This is only 400 parsec away. Yeah. Because the size is so small. We're talking about 40 AU. The younger ones are about 10 AUs only. The size, I mean, the radius of the disk, 10 AU. Yeah. It's not like a parsec scale. Yeah. It's AU scale, 100 AU scale.
Okay, that's
Yeah, you have to submit your proposals. They have this array schedule, different times and different arrays configuration, which give you different resolution. Yeah, they also the right extension of a source, where is the source position, right? So I think every 1 month or two, something they change to a different configuration. Yeah, and also this change, how frequent this configuration change demands from the user base. It depends how many proposal accepted in that for the configurations. Yeah, so usually it's dynamical scheduling. So they also depends on weather too. If your project require like better weather, yeah, then the then they will put you on a high priority or something. I'm not sure at the moment, but let's see. They put your project, and if someone have better priority, they'll put in front of you. They also depends on priority too. So they scheduling the project according to priorities. And if happen those weathers are good enough, so the project higher priority all carry out, then your project can go in. Yeah. Enjoy. You say enjoy? No, it's not enjoy. It's just like dynamically scheduled. Yeah. Depends on the weather too. Yeah.
Okay, thank you very much, Lee. It's been a very exciting presentation. We have seen latest new discoveries being presented on behalf of the School of Physics. Thank you, Professor, for your lecture.
Thank you. Yeah, thank you for having me.
Anyone who wish to ask further discussion may come, especially students.
Yeah. Please come. Yeah, if you have questions.
Can you open the previous slide? The previous slide.